Okay, so I think we can start and move on with the second presentation. So the speaker will be Nicolas Gast, who is a research associate at INRIA, so in France, since 2014. Prior to that, he obtained his PhD from Grenoble University and INRIA in 2010, and then he did a postdoc at EPFL. So many of us know him for his interest in theoretical and practical development around mean field limits, but his research interests are also quite broad, as you can see by the fact that he's part of the TPCs of many conferences, not only in performance evaluation, but also in machine learning, for instance. And so today, Nicolas will be talking about near optimal scheduling solutions for weakly coupled MDPs. So Nicolas, please go ahead.
Yeah, thanks a lot for the introduction, for the invitation, and thanks also to Ruba for the previous talk, because I think it might serve as an introduction to some of the things I'm going to talk about. So I'll start my talk with, say, two motivating examples, on which I'll come back later. And you see that they have lots of things in common. So the first motivation problem is what I call the applicant screening problem. And the idea is that, do you imagine that you want to hire someone, and you have n applicants and t rounds of interviews, and at each round you can interview a bunch of candidates. So meaning that there is a fraction alpha here, and you can interview, for instance, 10% of the candidates at each round. And at the end, the goal will be to maximize the expected quality of the candidates that you hire. And for instance, you want to hire 10% of these candidates. But during the interview, you can, try to find the best or the one that are not good, in order to avoid to have bad candidates at the end. And so the one way this can be modeled, and that we'll be using, is that each candidate has an unknown quality, Pn. And here, I assume a really simple model that when you interview someone, it gives a result 0 or 1. 0 meaning that the interview was not satisfying, and 1 what it was. And the result is just a Bernoulli random variable of priority Pn. And the goal of the decision maker would be to hire the highest Pn among these candidates. And so, as you'll see later, this can be essentially modeled by some Bayesian framework. And here there are kind of heuristics that you may find, like, do you want to be greedy, trying to find really the best candidate, or do you want to, interview lots of candidates to find the ones that are not good? And probably, you might say that, okay, this will depend on beta, if it's, or on t, if it's really small or really big. And what we'll talk about is like how to find the best solution here. The second motivation problem is really close to the previous talk. It's essentially almost the same as the job scheduling problem. And here the idea is like, what do you want to work on? We can think of this in terms of call center, but also in like research problems. You have a bunch of research problems that you want to work on, and by whom do you start? And as what's said in the previous talk, if we can model that as a queue. Okay, you have one server that is you, or maybe multiple servers. You have a bunch of jobs. And you can do things like preemption, like what was done in the first part of the previous talk. And this is some more reasonable model for quite a lot of, task allocation, but also you may think of like electrical vehicle charging. And so here the idea is that if you know exactly the duration here, these bars would be the duration of each task, it is quite well known that the optimal thing to do is SRPT, okay, shortest remaining processing time. And essentially this, you cannot do better. It's optimal in any sense that you may think about when you have a single server and when you know exactly the duration of the task and when there is no abandonment. which I mean is quite frequent in all of these things. Or for instance, in research project, if someone else is working on the same project as you, maybe you would like to finish before, and the project is only useful if you complete it first. So SRPT is optimal in many situations, but in general, it's not optimal because the constraints are violated. And so these two problems, they may seem a bit different, but they are what we call restless bandit problems. I will define more precisely what it is later, but say that for each cases, you have a bunch of resources in front of you, and at each time instant, you select a few of the resources, either to work on or to interview them or to activate them in some way. And the thing is that their states may evolve if you activate them or not. And this is what is this restless term that means? And so in general, these problems are really hard to solve. So there is a famous, I think, statistically Dimitriou paper from the 90s that show that these problems, when you know everything, are p-space hard, which is like harder than NP hard, essentially. And in general, lots of the approximation, heuristics that you may find, greedy, random, SRPT, are not optimal. Sometimes they may be asymptotically optimal in some medium, but in general, they are quite far from the optimum. And so the idea of what I want to talk about is how to construct policies that are close to optimal by assuming some sort of independence between the different resources that you have access to. And as you see, that what we are going to do is to build some policies that are asymptotically optimal in some regime. And they will be based on the solution of linear programming. So in the sense that you can say that they are computationally efficient, so they are efficient to compute. So here's what I'm going to talk more precisely. I will first talk about the finite horizon problem, which is motivated by my applicant screening problem. And then I'll move more to the infinite horizon here with these two sections, where the first one, I'll define what is the index policies. And in the second part, I will show you how to compute indices. So how to define and compute these index policies. And as I said before, I think do not hesitate to stop me at any time, to raise your hand if things are unclear, and I'll try to pause at some places. Okay, so I'll try to define in precise mathematical term the problems that we are studying today. Now, so I'm concerning what is called the multi-armed bandit problem. And so imagine that you are a decision maker, and in front of you, you have n what we will call arms. Okay, time is discrete to simplify the exposition. And each arm, in fact, is a MDP, for which I have two actions. Either we'll call it passive or active. So if you think in terms of job scheduling, passive means I'm not executing this job. I'm not serving it. And active would mean I'm serving it. If you think of the interview problem, passive is that I'm not interviewing, and active means I'm interviewing. And so we will make one sort of important thing, that you have a controller, and you can activate only a fraction of these arms at each time instant. So it's denoted alpha, the fraction here that I can activate. And it just means that, for instance, if I have one server and 10 tasks, I can activate only one task. So here alpha would be, for instance, 110. And so the job of the decision maker is that you observe the states of all of the arms in front of you. and which one do you activate? So here, when I said that an arm is an action MDP that has two actions, is what I mean is that all the arms evolve independently given the actions. Okay, and so it's a really, classical Markov decision process model that if you are in a state S and you take the action active, then you earn the reward R that depends on the state and the action, and you jump to a new S prime that depends on the state and the action. And the important thing here is that if you choose the passive action, the process may still jump to something else. And this is where we have this the term restless. Restless means essentially that P is in general not the identity matrix. Okay, and for instance, if you think of the abandonment problem before, this is a restless problem because your task may go out, may leave the system, so it may jump to the thing, I cannot serve this task anymore, even if you don't serve this task. Okay, so this is the term restless. Where there is lots of bandits are called that it's either rested. Classical Markovian bandits are either like rested or restful bandit, and in which case this P would be the identity matrix. Okay, and so when I say have these transition and rewards, I'm assuming that they are all independent through the different arms, but they are independent given the action. Okay, and what makes the problem complicated is that the constraint that I have on all my arms is a constraint that couples all the MDPs. I said that we are going to look at asymptotic regime. Here by asymptotic, I mean that we have n arms. We'll assume that they are all statistically identical. When I say that, I just mean that they all have the same reward function and transition matrices. Okay, and some places it will be convenient for me to use this thing. I will call like X and Y. X would be the fraction of arms that are in a state S at a given time, and Y essentially will be the fraction of arms that are in state S for which the action A is taken. Okay, I'll try to recall these notations, and here I'm using the superscript n because the asymptotic will be that I'm going to let n go to infinity in the top. So n is fixed throughout the time, but n I'll consider different settings and different problems that are indexed by this n, where I have this n arms. So now, because I have this X, X is my state of my state space, and Y would be my action space. What I'm focusing here is a policy pi that takes an X, okay, and that gives me a Y, okay. And what I will say that Y is feasible for this X, okay, if it satisfies this activation constraint. Okay, I'm missing an A here. And so the activation constraint, this is just to say I cannot activate more than alpha n arms at each time instance. Okay. And so here, what we are looking for is a policy that maximizes the reward among all the policies that satisfy this activation constraint. And as I said, finding the best admissible policy is known to be harder than NP hard. So, essentially, this is just a computational problem, because I'm going to assume through the talk that for now I know all the parameters of the system. But the thing is that here the policy is takes a vector x. Okay, so the policy pi t, it takes a vector x, and x is like x1 to the xn. and this gives some vector y. And the thing is that the state space of this Markov decision process is just enormous because it grows exponentially with the number of component n. So here, my problem that I'm looking at is really, it's a bandit problem, not in the learning sense, but more in the Markov decision process sense. And that's where we want to compute a policy that is close to optimal, but we cannot because the state space is just too big. And so one way to construct policies for this is to replace this activation constraint. So the activation constraint, recall that it's just, okay, I'll forget an A again, is that on average, no, sorry, not average, but you should not activate more than alpha n arms at every time instant. So the activation constraint here is like for all t, you cannot activate more than alpha n. And so to build some policies, one of the things that has been done for the years, and it's we'll see, like if for those who know Whittle index, I'm just anticipating a bit, but this is related to the Whittle index. The idea is that you will replace this constraint that is annoying because it couples all the Markov decision processes, all the arms, by a constraint that is simpler, and that is on average, I cannot activate more than alpha n arms. Okay, and so my constraint becomes for all t, the expected number of activated arms cannot be larger than alpha n. And so just to say something about, so this problem with this constraint was NP hard. The problem with this constraint, okay, can be solved by a linear program. Okay, so just let me give you some, brief proof. When I say proof, it's just just a way, and to solve this problem. It's just a pure rewriting. It's like here, what I'm using is that the variables y s a of t would, small y would be the expectation of these variables, and just the x would be the expectation of these the state variables. And maybe you can just believe me, but that the whole optimization problem is just can be reformulated as this linear programming, where the first line, of course, is the maximization of the reward. The second line is the relaxed activation constraint. The third line is the Markovian evolution, and this is just to say that the expected number of arms in state S prime would be the sum of over all state and action of the expected number of arms in state S and action A multiplied by the probability to jump to this S prime. Okay, and the last thing is just the is just to say that you have to choose one action per arm. Okay, the last quantity is just you have to choose one action per arm. And so, okay, this gives a way to solve this problem. Okay, now it does not really give you a way to solve the original problem, right? It's just some other thing. And so here is where we stand for now, that we have this original problem where we have the strict activation constraint, and we use some relaxation, and what we have is an LPs. We can write an LP that can be solved, and that solve the optimal problem here. And so, of course, here, if V star n would be the optimal value for my problem with n arms, what I call V star rel, which is the optimal value for my relaxed problem, this V star L will be larger than the original V star L. And also, I did not write, this doesn't depend on N here, okay? Just because I assume that all the arms are independent, if you look for the equation, this doesn't depend on N. And so now, okay, to obtain this V star L, what we can do, we can solve the LP, and this gives us a trajectory that I'll call X star, Y star. Here, the small letters just mean the deterministic letters. And so what we want is we start from this X star, Y star, and we want to build a policy, okay, that if possible is close to this optimal policy, okay? And the question here would be like how to build, can we build such a policy? Does it become optimal? If yes, under which conditions? At what rate? When S goes to infinity, etc., etc. And this is subject of a few recent papers. One of them is ours that focus on this finite horizon restless bandit problems. Okay, so now let me try to explain you. Okay, we have this here an optimal sequence computed by this linear program that I call X star and Y star, and we want to find a sequence of policies, and a policy is something that takes any possible X, okay, and that gives a Y that is admissible, meaning that the Y has to satisfy all the constraints of the original problem, not the relaxed one. Okay, and what we are going to say is that I'm going to say that okay, a sequence of a policy here pi is compatible if when you apply pi t to X star of t, you get exactly the Y star of t. Okay.
Nicolas?
Yes.
Sorry, there's just one question in someone
Sure.
raised their hand. So it's Albert. I think that he can unmute himself.
Yeah. Hello?
Yep.
Yes.
Yeah. My question was about, so here to solve the linear program, you assume that you know the transition probability, right? Is this common in restless bandits?
Okay, so let me rephrase the question so that I hear it well. But you are asking like to solve the linear program, am I assuming that I know all the transition probabilities? And the answer is yes. And is it common in for restless bandit? In fact, there are the thing that if you want to solve these problems optimally, you need to know the transition probabilities and rewards, and this is already a hard problem. Then there is some complementary branch of the literature that says, okay, how can we estimate these probabilities, and how can we learn them by doing some no-regret algorithms? And somehow knowing what is an optimal or close to optimal policy is useful when you want to devise some learning algorithm for this restless bandit. But yeah, I would say that the true problems are studied. If it answers the question.
Okay, thank you.
Yeah, thanks a lot for the question. Okay, so here, yeah, we are really working on this computational problem, that is, can we find this optimal policy? And now, okay, I'm just saying what I said, that a policy is LP compatible if it takes the same decision as the LP when the state is the same as the state predicted by the LP. And in fact, it's not really complicated to show that a policy is LP compatible if and only if it is asymptotically optimal. Okay. And in particular, if you have what is a bit more tricky to show is that in general, the convergence rate here that it occurs at rate like 1/square root of n. But if you have some what we call local linear properties of the policy, So if the policy pi is locally linear around this X star, we can show that the convergence holds at exponential rate. Okay. I'm not going to prove this result because it's, I mean, it's both really simple, and it just uses this idea that the stochastic system Xn converges to a deterministic limit. Okay, and this is due to the continuity of the policy. And therefore, the reward of the stochastic system converges to the reward of the deterministic limit. Okay, and now, I mean, somehow this pi here is optimal only if it is LP compatible. So that's the rough idea. The second part is more complicated, but I won't go into details here. Now, okay, what I'm just saying that if there is a continuous policy that is LP compatible, then it's asymptotically optimal. But there remains still this question like how to build this policy. And for that, I will use this kind of drawings made by my students, and I hope you will understand them and you will find them nice. Okay, just to explain you what is the problem here. Here, what I have on the top is X star is how many arms do I have in different states, okay? And so I have many arms in these states, fewer arms in state, and not so many arms in these states, okay? And here, if you look at the blue lines here, for instance, this one, this for the first state means that I'm choosing action active for all the arms in this particular state, and also for this one. And here there is a red line, so I'm just choosing the active action for only a part of this state. Okay, and here I'm not activating any of the arms that are in this and that state. So the first thing, this is the LP solution. And now I have a second solution below. And what you see is that there is one thing is that in general, Xn will not be equal to X star, okay? And this is just illustrated by the fact that the boxes are of different size, okay? This boxes here is larger than the boxes below, okay? And so I'm just ordering my state like, okay, S plus, S0, S minus. S plus are the boxes are full. S0, they are half full. And S minus, they are completely empty. And now the idea is that I'm using some what's called water filling policy. And I'm just saying, okay, I will fill first these boxes, then the boxes up to the red, up to the red horizontal line. And you see that here the red horizontal line is at the top. And then I fill them later on. And okay, so this what will give you, I give priority to S plus, then the second priority to S0 up to these red lines, okay? And then after that, if I have some water left, so if I have some budget alpha left, I fill the rest of the boxes, so this one, and maybe later on this one. And so it's relatively intuitive to realize that, okay, if X star is exactly equal to Xn, then it gives exactly the same solution. Second, this is clearly continuous in the box sizes, okay? And the third thing is that that is a bit less obvious is that if there are some states in S0, so if some of the boxes are half empty, the function that you obtain is linear in the state space. Okay, this I won't go to that, but this is so if S0 is not empty, the pi t that goes from X to Y is locally linear. Okay, and so this, allows us to go back to the previous theorem and just to say that for any problem, there exists an LP-compatible policy given by the water filling here. If the problem is what we call non-degenerate, meaning that the number of states in S0 is larger than 1, then there exists a locally linear LP-compatible policy. Hence, we have some exponential convergence rate for this water filling policy. And the last thing is that if there is at most one state is in S0, the problem is what we call rankable, meaning that it's just a strict priority policy. And somehow this is an if and only if condition, like the problem is rankable if and only if there exists a strict priority policy that is asymptotically optimal. Okay, so let me try to go back to the example to stay where we stand and to make some easier math. So I'm going back to the applicant screening problem, and what I want to show you here is how does this problem look like and what is the relation with this LP solution. Now, the idea is that I'll assume that all candidates have some quality Pn. This Pn is the quality of candidate M. And what I will look at is some Bayesian model where I have a prior on the quality of the candidates. And this prior is beta 1,1. So before I start interviewing them, I consider that all the Pns might be anything between 0 and 1, and the distribution of Pns is uniform. And so here the state of a candidate at the beginning, it's 1, 1, okay? If I don't interview this candidate, it's 1, 1. And now if you interview a candidate, okay, if you have no interview here, the state remains 1, 1, okay? Now, if you have an interview, a positive interview, what we have is that the posterior distribution becomes a beta 2, 1, and this occurs with priority 0, 5. And if you have a negative interview, the posterior distribution becomes 1, 2, etc. And if you have 2, 1 and you get a positive interview, then you will get to 3, 1, and this occurs with priority 2, 3, 1, 3, okay, 2, 2. And so you have this, this thing that probably maybe all of you know and teach to their students. You have this classical posterior probability. And so this gives, this thing gives the Markov chain evolution of the candidate. And now the question that becomes is that we first start with n candidates that are all in 1, 1. So of course, at the beginning, we interview any of these n candidates. And now after a first decision time, we will have a few candidates that are in 2, 1, another candidates that are in 1, 2, other candidates that are in 1, 1. And who should I interview? And this, I hope that you like this picture. This is a visualization of this the LP solution that you'll find this in this paper. Where here at the beginning you have this candidate that are 1, 1, and these are the 2, 1s. These are the 1, 2. And what this thing tells you is that okay, at first you interview all the candidates that are in 1, 1. And then on the second round, you don't interview anymore the candidates that are in 1, 2. You just they will just go there. But you will interview, and you don't interview, the candidates that are in 2, 1. Here, you interview only the candidates that are in 1, 1 again. And then it leads you to another state that you have candidates in either 2, 1, 1, 1, or 1, 2. And here now you start mixing a bit of these candidates in 1, 1 and a bit of the 2, 1s. And not all of these candidates. And so this is where this problem is not rankable because you interview a bit of these and a bit of these. And after a while, the LP solution gives you exactly how many candidates you should interview. And for instance, here at time after 2 interviews, you should interview somehow half of the budget for these candidates and half of the budget for the candidates into one. Okay. And just quick numerical results. What I told you at the beginning that what we are looking at are policies that become asymptotically optimal as the n grows, so here as the number of candidates grows. And so here on the x-axis, I'm putting n, and on the y-axis, I'm putting the average quality of candidate that I'm having. And the dashed line at the top is my relaxed upper bound. And what you see is that essentially the two LP-based policies here, the two LP-compatible policies that are here, are both asymptotically optimal as n grows. Which means that they are, they are both converging to this relaxed upper bound, so they are both asymptotically optimal because this is an upper bound on the performance. But still, there are some differences for smaller values of n between these green policies and these orange policies that are two LP compatible policies, but one may perform better. And the thing is that probably the Vn star, the performance of the relaxed, the optimal performance of the policy is probably in fact not too far from this green curve, but essentially the only thing that we know is that it's below this thing, and this is computationally impossible to compute even. Maybe for this point we could compute, but already for 10 that is like 20, it's essentially impossible to compute. Okay, so this was all I wanted to say about finite horizon. So I'm realizing that maybe I'm running a bit out of time, but yeah, the next part is a bit shorter. But if you have questions, again, do not hesitate.
There's one question from Michel.
Yep.
So Nicolas, in your proof regarding the difference between the original problem and your mean-based LP, it didn't seem that you are really using the specifics of the models that you are discussing. Am I right? And if yes, to what level can you extend this result?
Yeah, so the main thing that we are using here are that the we use that the arms are independent given the actions. This is to and this has two roles. Say one first is to obtain some concentration argument. Okay, so the same thing as you would do for any kind of mean field interacting models. Okay, and the second thing is that this is crucial when you want to obtain some linearity property. And the fact that the x at time t plus 1, the expectation of x at time t plus 1 is a linear function of the expectation of y at time t. And why this is important, essentially this is important when you want to prove the exponential convergence rate. I didn't go into details like this, but this is where really we have this independence. But so essentially the main assumption that we are using is that the arms are local MDPs and they are independent given the action. Now, I did not present it here, but for instance, you can extend this problem to multi-actions or to multiple constraints. It would give the same thing. Okay, as long as the arms are independent given the action.
Okay, thank you.
Okay, so maybe to conclude, let me just give you a link between what I've presented and this whole idea of Whittle index, Keating's index, and where these things are optimal. So the idea that I used for now is that we have some constraint that we relaxed. Okay. Now, okay, here I'm using some equality constraint, but it doesn't really matters, didn't really change anything. But the idea is that we replace this exact constraint by some equality constraint where we have this expectation. And now the idea that is quite classical in linear programming is to use some Lagrangian decomposition of the problem and say, okay, this is a constraint that in my LP, I can just replace it by some subsidy. So in a sense, instead of writing this complete thing, I would write this constraint as, say, mu times sum of all state and arm and of this expectation of A YSA minus alpha. And so what this becomes is that if you choose action A, this costs you mu times A. Okay. So the idea is that I had my original problem where I have a reward RS active for when I choose the action active. And now I'm moving it to this cost or earns, different issue, minus mu or plus mu. There is a subsidy here, mu, for the active action. Okay, and you look at now this new problem, that is the subsidized problem. And what will happen is that in general, the optimal policy will depend on the subsidy that you put here. And especially if mu is minus infinity or almost minus infinity, then the active action will never be optimal. And if mu is essentially plus infinity, then the passive action will never be optimal. And so here, I'm just using I'm looking at this infinite horizon problem, and so to avoid any dependence on time. Now, if you look at this LP program, I say that this is a relaxed version, and so in general, the optimal, I mean, mu is a Lagrange multiplier. So in general, this optimal mu will depend on the budget alpha. And so there is one idea that came, I think, with Whittle, which was to find some way to overcome this difficulty. And so here I'm just trying to define what is this indexability. So here, what I plot on this graph on the x-axis is the subsidy mu for the active action. And here below is some representation that would say that, okay, S1, choosing the action active is optimal up to that point, okay, for S1, up to the subsidy mu that is here, and choosing the action activate is optimal up to that point, or to that point, or up to that point, okay. And so what I've said before is that if you want to solve the relax problem, probably there is an optimal. Somehow there is some mu star that is the Lagrangian multiplier, and that says, okay, you should activate all the all the states that are above this mu star, and you should not activate the states that are below. And so the idea of the Whittle index is to say, okay, when the problem is well behaved, meaning that when there is when for all states there is a clear things that say, okay, here for state 4 it's optimal to activate. Oh, okay, if it's a subsidy, probably it's optimal to not activate before, and it's optimal to activate after this. When for all these states there exists like one particular value that makes it optimal to activate or not activate before or after this value, then we say that the system is indexable. And what we will do is that we will activate the state in increasing or decreasing order of priority, depending if we want to maximize or minimize. And for instance, here it would be that just the state S3 has a larger index than state S1, that is larger than state S4, that is larger than state S2. Okay. And essentially, you can apply the same reasoning as I did before to show that any policies that activate, above this the optimal threshold mu star will be LP compatible, hence will be optimal. And in particular, the Whittle index that activates first this one, then this one, then this one, then this one, will also be asymptotically optimal under some, under some technical assumption of global attractor fixed point, but that is essentially always true, except for really, really particular counterexamples that you need to construct manually. Okay, maybe I won't really talk about how to compute this, but rather just to say, so give you some illustration and to go back to the scheduling problems, and to give you again a sense of what are these Whittle or Gittings index. And here, so I'm considering that you have jobs for which you don't know the size exactly, okay? But you know the distribution of the job sizes. And for instance, the first job has a size 10 minus epsilon, so you know exactly the size of this job. And for the second job, the job Y, it's either 2 or 18, but you don't know exactly if it will be 2 or 18, and it's probably with priority 1/2 it will be 2, with priority 1/2 it will be 8. And so the first job has a smaller expected service duration than the second job, okay? So a natural policy would be to say, okay, let's serve the first job first, and then let's serve the Y job. Except that the second job is quite likely to finish after just 2. So maybe a more smarter policy is to say, okay, let's serve the first job Y for 2 time steps. Okay, and if this job finishes, then we're good. And if after 2 time steps the job did not finish, then we can start instead the job X. I mean, given that if we can allow some preemptive scheduling. And this policy essentially called Gittings policy. And the idea is that you can extend this to any kind of distribution. And the idea is as follows: that you consider that running a job costs you say €1 per second, and you will find the penalty of the subsidy X. That is if you finish the job, you earn X, which was my mu before. And the Gittings index will be the smallest X, so that at time 0 or at a given time, running or stopping is equivalent. What does this mean here? That now assume that my first job is X as 10, and now I'm looking at my x-axis is the age of the job, and on the y-axis I put the index, given the age. And so the idea is just that at time 0, you know that if you start running the job, it will essentially cost you 10 before it can finish. So at time 0, I have to promise you 10 if you want to start running the job. But at time 5, you know that you already run the job for 5, so the remaining processing time is just 5. So here, the idea is that for the blue job, it will be at 5. If I promise you 10 at 5, you say, of course, I'll run the job. I have only 5 remaining. But if I promise you less than 5, you will not run it. So the equality is for 5. And so it's just a straight line. Whereas for the second job, the job Y is a bit different. That at time 0, if I promise you 4, you say, I can run it now for 2 time instants because I can stop after that. So you will start running it, and at time 2, you realize that its Gittings index will be 0 because here you really want to start the job, and just after that, essentially it will jump to something way higher, and it will go back like this. And this is what you will get as getting index, and then the policy would say, okay, you should first start the red job if you have one, as long as it is here, and then here when you have a job like here, you should only run it before that if it's essentially if it's not if they are comparable. Okay, so I think I should probably stop there. Was just going to say, in fact, there are many things that these index policies have been there since the 70s, and said a lot until the 90s. Then there, we've seen before in the previous talk that there are lots of studies of getting the index, analyzing this performance, the link with SRPT, are they close to optimal, etc. That occurs. And in fact, there are also quite a lot of more recent papers about like the optimality of this index, regret learning algorithm, finite reason problem that have been done there. And one of the last thing I wanted to present, but I won't have time, is that in fact, it is not, it's computationally easy, relatively easy to compute this index when the state space of your project, of your arms is finite. Okay, so I think I should stop here, and maybe there is time for questions. I don't know.